If you don't know CMC Microsystems, we're here to help with your product development. So we support microelectronics, photonics, MEMS, nanofab, AI and machine learning, and quantum technologies. We have over 50 people doing technical support for you. So if there's any way we can help, that's great. And most of what we do, about half of what we do is supporting a major science initiative in Canada, one of 16, which is called Canada's National Design Network. So it includes 67 universities and colleges and about 1,000 companies. And the real idea is to design, build, and test micro and nano systems. We offer services in 3 areas: CAD, Fab, and Lab. CAD is software. I'll talk a bit more about what we offer to industry. Fab is multi-project wafer services. So we offer everything down to 12 nanometer FinFET. We offer photonics manufacturing, MEMS manufacturing, and we're just working with some partners now on doing an RF device in 22 nanometer from Global Foundries, and it has FTs of 300 gigs. So you can do some really interesting stuff in the 40, 60 gig range with some of the processes we offer. CMC purchases the minimum volume, and then we put as many customers on there as we can to cost share. So it's a great way for you to do R&D and develop new ideas. We also have an equipment rental program. So most of the time the gear is out to academics, but when it's available, industry can also use it. We have a 90 gig LNA. We have a 250 gig real-time scope. And we support about 80 different pieces of gear. It's all available on our website at cmc.ca. We also develop technology platforms. So we have a number of them. There's a photonics toolkit. There's a sensing device for chemistry, biochemistry, and an interposer device, which we use to mount chips directly without packaging onto a single substrate. For industry, we offer this virtual incubator environment for SMEs. Up to roughly 5 million in sales, you're still eligible. And there's CAD that's included at just about the academic price. So very, very inexpensive CAD. The Fab access, obviously, and then we have a number of different systems that you can access as a V customer. It's an annual fee of $2,000. And that's it. Thanks to our funders. And thank you very much. I would like now to introduce our speaker. That is Nikhil Adnani from ThinkRF. He has over 25 years of experience in the area of wireless. He has a BSc and an MSc from the University of Manitoba, but then he saw the light and came to Carleton for his PhD in electrical engineering. And he's held engineering positions at Nortel and the CRC, Communications Research Center in Ottawa. And now he's been with ThinkRF since, 10, 15 years now.
Okay, thanks, Gordon. Thank you for that kind introduction. I hope you guys can hear me okay. Okay, so thank you everyone for joining today. Really excited to be here to bring you this presentation on July 15 today. So ThinkRF has been in the business of receivers, software-defined radio receivers, for over a decade now. We've had the pleasure of working with a number of companies, big and small, federal governments worldwide, telecom companies, R&D organizations, and others. We've dedicated our engineering effort to working on these receivers, every aspect of these receivers. And so today I'm going to talk to you about key requirements for small receivers and the rationale behind it. So an overview of our presentation today, speaking to the growth of wireless, and follow that up by spectrum monitoring. Like, why exactly do we need spectrum monitoring? What is the future of spectrum monitoring? Key requirements for it, and then some of the main challenges around what the future, challenges around solving the problems of the future as it relates to spectrum through these receivers. Followed by some real-world use cases, nothing like showing you what people actually use these receivers for today, and followed by a summary, and then we'll have a Q&A session with questions from you guys. So without further ado, so this is a little picture of what wireless looks like today. So starting in 1987, we had the advent of the first generation of wireless networks. These operate at 800 megahertz, very narrow band for amps channels, 30 kilohertz. And for the past, over 30 years, we've been largely evolving technology in the area of cellular communications, moving from 1G all the way up to 4G, which is still being deployed. Actually, 4G is still being deployed in large numbers now with private LTE networks, and that has all been under 3 gigahertz. Okay, and our bandwidths have evolved from the 30 kilohertz to up to 20 megahertz. Now, starting 2019, we're seeing a big jump, both by way of frequency of operation, so all the way up to 40 gigahertz, and bandwidths as well, all the way up to 2 gigahertz. All this is being done to satisfy demand. We've got growth in requirements for data. People want connectivity everywhere and anywhere. And that is going to be addressed by 5G, okay, with mmWave deployments and others. So a really exciting time for us, really challenging time as well, because we're now stepping into territory that we've never been in before with these wide bandwidths and higher frequency ranges. So everything was, we got to understand these sub 6 gigahertz, sub 2 gigahertz network, 3 gigahertz networks, if you will, for cellular. We've had the benefit of 30 years to do that. And now all of a sudden we're jumping to mmWave, which, as many of you know, is challenging from many standpoints, propagation and otherwise. So it will be definitely an exciting time. Okay, now 5G gets a lot of airplay, but let's talk about other technologies. So there's IoT that's growing rapidly. Everyone has at least one, if not many, IoT devices around them, starting with your smart watches to your Sonos speakers and other such devices. So needless to say, the growth is tremendous. Okay, this is from Cisco, their predictions on M2M, and obviously the biggest share of this is actually in the connected home, right? The growth rates are pretty impressive. And moving ahead, we're going to see growth in connected car and other areas as well. Okay, so anytime somebody says exponential growth, I always think back to this little picture I saw a while ago, where the actual use of the phrase exponential growth has been growing exponentially. So, but obviously, that's truly the case in wireless, where we're actually seeing true exponential growth. Now let's take a look at some other use cases in wireless. Okay, we're seeing illegal use cases, those that are not definitely far from legal, by way of jammers, for instance. Right, we've got jammers that are this is something of a website, non-US website, obviously, where the sale of these jammers is permitted. However, some of these devices do make their way. Many of them make their way into North America, where it's definitely not legal to jam these networks. So people use these to jam GPS networks, 3G, 4G, and the like. Okay, but definitely far from legal. Okay, so really, you've got the growth in wireless, and you've also got growth in devices that are used to inhibit wireless. Now, this is, a very intentional inhibition, or rather disruption, the intent to disrupt. But over the past year, we've actually seen some very interesting use cases as a result of the pandemic, even, that inadvertently disrupt communications. So we've seen proliferation of drive-in churches, drive-in movie theaters, and some older use cases as well, where you have anybody who's driven up to a Christmas lights display and turned on their FM radio to tune in. That's another potentially inadvertent method to disrupt communication. And all, this is all just to delve a little further into this. This is a device that's actually sold on Amazon today, right? It's a 15-watt FM transmitter, definitely way more power than it's beyond the legal limit. And people have reported having success, proudly reported having success with these in the tens of miles of range. right? And the actual limit, if you look at the North American FCC and ICED, is actually about 150 feet. So the FM signal from these devices should not propagate further than that. So definitely very disruptive. Okay, so needless to say, the wireless environment is getting very complex. Okay, you've got really complex modulation formats through increasingly complex with 5G. You've got the wider bandwidths, the higher frequency ranges. You've got smart cities. You've got wireless everywhere. You've got bad actors trying to disrupt communications. So through the use of jammers, as I mentioned. And you've also got, good people, as you might say, who are inadvertently disrupting communications. So really, this truly is a problem or a situation rather, that's growing over time, truly exponentially. Okay, so why monitor spectrum? Okay, that's the question. So when I say monitor spectrum, what I mean is in some way, shape, or form, observing the electromagnetic environment. Okay, watching the RF spectrum. Okay, there are two main use cases. Okay, one is preventing illegal use, whether that be intentional or unintentional, and optimizing performance. So many times people monitor spectrum to improve the performance of their networks. Sometimes these are related. So you can have performance degradation due to jamming or other situations, but many times they're decoupled. Okay, so that really is the primary rationale for monitoring spectrum. Okay, so let's take a look at spectrum monitoring today. Okay, what is it? So spectrum monitoring involves, in many geographies, it involves getting a complaint from a stakeholder, somebody who owns the spectrum, and somebody, whether it be the stakeholder, the spectrum owner themselves, or a regulatory body, driving out and hunting down the source of interference. Okay, so that's in very simple terms, that's what it means. So hunting it down and shutting it down. Okay, so it's definitely at a high level, that's what it is. It's more complex than that, obviously, when you get down to it. So one of these trucks, this is an example truck from a spectrum monitoring organization, and what does it include? So you open the doors at the back, and you'll see a rack, typically of spectrum monitoring equipment. Either by way of PXI devices or spectrum analyzers. And also coupled with that is potentially one or two handheld units that's used to narrow down on the source of interference. So to actually find out in a more granular way where that interference might be. Okay, so that's what it is at a high level. But you can imagine, with today's environment, by the time you go out to hunt down the source of interference, it may no longer be there. So this is a very, if you might say, a reactive approach. So you get a call, you go out there, you respond to it, and hunt for it effectively. So it's called interference hunting. Okay, so let's take a look at what the future looks like for spectrum monitoring. Okay, in this new environment that I described earlier. So we have a whole lot of new today. Okay, we have devices that never existed 10 years ago. Okay, you have smart speakers, you have self-driving cars and connected vehicles that are growing in their market entry. They're entering the market right now. You have drones. About 15 years ago, these drones had very specific use cases. They were not in consumer territory, but now they are. You've got smart watches, smartphones, obviously, and a number of other such devices. Okay, now these devices never existed. Like I said, even Wi-Fi access points, you had 802.11, which was A or B, which was narrower in bandwidth. Now we've got to 802.11 AC, which is much wider in bandwidth, about 160 megahertz in bandwidth. So the amount of wireless is growing, the bandwidth use is growing, and you got wireless everywhere. So what does spectrum monitoring look like in this new environment? Okay, so in this new environment, in the not too distant future, we at ThinkRF believe that it is distributed and persistent. Okay, and we've seen a growing market for this newer type of spectrum monitoring requirement and outlay, if you will. Okay, so what are the key requirements of a system like this? Okay, the first one is signal measurement. It's got to be able to measure signals in a geographically distributed way. Okay, so essentially you have devices all over the city, and you've got to be able to measure them because these are intermittent signals. They come and go at when you come and go when you least expect them. So you have to be able to detect these, okay, in case of interference events. You've got a need for analyzing the signal. So you've got to look deeper to identify whether it is in fact an interferer or if it is, just part of the signaling environment, the expected signaling environment. Okay, you've got to have real world operation. Obviously, these devices that you put out there to monitor spectrum have to be able to operate in the real world. Okay, and I'll get into more detail on this a little bit further. You've got to be able to measure or figure out where the transmitter is located. So if you've got a jammer, you've got to be able to figure out where it is so that you can shut it down. And obviously, the network that you put out there has to be distributed. You can't have and always on. So distributed and persistent. You can't have these reactionary type approaches to spectrum monitoring because signals are complex, they come and go. By the time you get there, it may not be there. So you're essentially playing a game of whack-a-mole there, right? Which can lead to very low probability of success. Size, weight, and power, your devices have to be small. They cannot cost a lot, obviously, because you cannot deploy in large numbers anything that's too expensive. Okay, so let's take a look at the current category of products, if you will. We have benchtop spectrum analyzers, and what I've done is I've put this within the context of the requirements on the previous slide. So these are excellent these devices are excellent, or instruments are very good when it comes to signal measurement and wideband signal analysis. These have been scaling proportionately to address the needs of 5G, real-time spectrum analyzers, PXI devices, and even the handheld devices. But when it comes to real-world operation, they don't always, you can't drop these in the field and place them in the field, for instance. You cannot generally locate transmitters easily. I mean, you've got to go out there and on an interference hunting mission, but you cannot do that with a benchtop. And typically the handheld instruments don't have the specifications of a benchtop. So really you're going out, if you're doing transmitter locations with a handheld, it's not going to have the same measurement capability that something like a benchtop has. Okay, and these devices can't be distributed or networked easily. That's not what they were designed to do. So they cannot be deployed or scaled, in a scalable fashion. And finally, the size, weight, and power, needless to say, these are pretty big and bulky devices. So you can't really, they're not where we need them to be from that standpoint. And cost, I mean, these devices like the real-time spectrum analyzers that analyze 5G waveforms cost anywhere upwards of $50,000 at the very minimum, right? They're upward, typically closer to $80,000. So that's not a price point that makes it scalable. Okay, now let's take a look at the other end of things. So the low-cost software-defined radios, these have gained in prominence lately. They've gained in popularity. They're used for a number of very application-specific. They're used for very specific applications. Okay, so if you want to do things like AIS monitoring, or ADS monitoring, these devices are very good for that capability. Okay, but when it comes to actual signal measurement or wideband signal analysis, they don't do very well. These are typically restricted to about 20 meg at the most, 20 meg of instantaneous bandwidth, and that's much lower than where we need to be for something like 5G, and they barely make it at 4G, right? So they're definitely not good for that. Where they really excel is in the size, weight, and power. These are USB devices, very small, very cost-effective too. You can buy these for anywhere between $25 to $300, right? So very cost-effective. But when it comes to real-world operation, they don't meet those requirements. And I will get into a little more detail on this later in the presentation as well. When it comes to transmitter location, because they don't have the radio specifications or the RF specifications, it becomes very difficult to apply these for true TDOA type analysis, or anything where you want to determine a transmitter location with accuracy. And finally, they're not designed to be networked. All of these in the examples here have USB ports, and to actually get them onto a network, you have to do a lot of configuration or development. Okay, so they're not out of the box network ready. So at ThinkRF, we thought about these problems we've been thinking about them for quite a while, working on them, addressing them through our products. And we have a product, a real-time spectrum analyzer that was designed specifically for this purpose of spectrum monitoring, for distributed spectrum monitoring. So when it comes to signal measurement and analysis, it has up to 100 meg of instantaneous bandwidth. It's designed for real-world operation. So it's designed to be fanless, field deployable. And also it has the hooks for transmitter geolocation. So we have a GPS port as well as the triggers that give you the ability to locate a transmitter with a high level of accuracy. The network port makes it distributable, so you can actually plug these into a network port or into a router and access them wirelessly from anywhere in the world. And when it comes to size, weight, power, and cost, these are definitely a fraction of the cost of a benchtop analyzer. They're not at the $300 price point, which is what I described, but they're not at the $100,000 price point either. So they achieve a price performance that is very suitable for the application they're trying to address. Okay, so when it comes to radio receivers, getting into some more technical detail, the core element of the spectrum analyzers and the software-defined radios is actually a radio receiver. Okay, the only difference between the benchtop and the handheld and the software-defined radio are in the architecture of the product, the implementation. So how well have you implemented the architecture? And as a result of that implementation, what are the specifications you're able to achieve? And this is really important because in any node or in any sensing device, any spectrum analyzer, it's garbage in, garbage out. So if you're not going to sense the signal with accuracy, with the required fidelity, you're listening to it, but you're not really going to be able to interpret or measure the signal. So it truly is garbage out. So let's talk about some of the important elements now of receiver performance. I've got 5 here. There are obviously many more, but these are the 5 main areas of importance. The first one, obviously, the first 2, if you will, are frequency range and bandwidth. Okay, so frequency range, I showed you in my first slide that we're going into completely new uncharted territory, 5G millimeter wave. You need the ability to get out there in terms of frequency range. So the ability to go to 40 gigahertz. Okay, and you need a bandwidth that's consistent with modern waveforms. So if you want to measure modern waveforms, you obviously need to be able to, your receiver needs to have the appropriate bandwidth. Just for comparison, the older analog spectrum analyzers, very narrow band, not meant to do modulation analysis of any in any way, shape, or form. The advent of the VSA and the RTSA gives you the ability to actually analyze these signals, demodulate them. Okay, next is dynamic range. This is an important parameter in the real world. It allows you to detect weak signals in the presence of strong ones. So if you're sitting right under a base station, for example, your receiver can be overwhelmed by the strong signals, so much so that you're unable to detect a weak one. And that's not good, because you really want to be able to detect the true diversity, a lot of different types of signals with your analyzer. So you don't want any one signal overwhelming it. Okay, linearity. If just as the name suggests, it's a measure of how linear your system is. So it allows measurement of strong signals. If you have a strong signal coming into this receiver and your receiver saturates, well, you don't have a good measure of how strong that signal is. So you want your device to be as linear as possible. Okay, sensitivity. This is an attribute of the analyzer that allows you to measure really weak signals. So when you go on interference hunting missions, you really, you encounter weak signals. That's because they may be far away from you, but you still need to be able to detect them such that, they get stronger as you move in that direction. And also you're able to actually see that that there's actually something there. If you have a noise floor that's very high, as is the case in many of these software-defined radios and spectrum analyzers, that noise floor masks a weak signal, so you can't see it anymore. And finally, spurious artifacts. Now, many of the spectrum analyzers and receivers, all the receiving devices have internally generated spurs, spurious artifacts, or we call them spurs. And what that is an internally generated signal that could fool the user into believing that there's an external signal at that frequency. But that's not the case. It's actually generated by the receiver itself. So you want to minimize these spurious artifacts or the spurs. So RF performance really is a key enabler. Okay, all these attributes that I've mentioned and more, they're very easy to achieve, or relatively easy to achieve, when you don't have as many constraints. And by that, I mean if you have a large device with a lot of room between, to operate in, it's easier to achieve all these specs. So to give you a good example of that, you're able to put in a lot more signal processing into it for bandwidth. You're able to put wider band digitizers into this, and you have big cooling systems that take care of the heat generated as a result of that. When it comes to spurs, as I mentioned, the further apart you're able to move your internal circuitry, the easier it is to mitigate interference from one section of the circuit to another, and thereby you can minimize spurs. A lot more difficult to do in a small form factor. Okay, so those are some of the key differences. So this is at a high level the big difference. It's but when you want to build a device for distributed monitoring, these are some of the hard problems you've got to solve in any receiver, right? So frequency range, bandwidth, dynamic range, linearity, sensitivity, and spurs. Okay, there are more attributes that I haven't mentioned here, as in how fast are you moving the data off the device, another key critical parameter, because the faster you move the device, the wider bandwidth you're able to address, the wider bandwidth of signals. So big, this really is the key challenge that ThinkRF has been working on. Okay, so let's get into a little bit on the architectures, with direct conversion being one of them. Now, I'll discuss three main architectures here. Direct conversion receivers are one of the most popular types of receivers. They're used in single chip solutions from the likes of Analog Devices and others. And they're really very optimal when it comes to a certain type of application. So the pros of these receivers, they're wideband. It's relatively easy to achieve wideband performance with this direct conversion architecture. they have relatively low cost of implementation, and the associated circuitry can be small. It's often stated that it's small, but given some of the limitations in terms of frequency range, if you actually limit the frequency range, it can be small. When you actually try and frequency extend these direct conversion receivers, then that tends to be not the case. So now let's take a look at some of the cons. These devices have issues around IQ imbalance. So the I and Q signals out of these direct conversion receivers can have a certain amount of imbalance associated with them, which in turn affects modulation or demodulation quality. They have DC offsets. So when you down convert the signal to a baseband frequency of 0, there is a finite amount of DC, and that can actually have impact on modulation that are sensitive to DC. Some examples of that are GSM and now even 5G, where information, depending on mode of operation, can actually be transmitted at 0 frequency. So these are some of the things you've got to be really careful about. The others are LO radiation. So the LO can radiate out of the RF input port and present a problem for, from an FCC or an ISET standpoint for radiation. And it has other impacts as well related to this. And so, when somebody implements a receiver like this in something like a hack RF or an RTL SDR, it's not, they're not really looking at these issues. They're not designed for precision measurements, right? They're designed for narrow band and measurements to a certain level of performance. So it's okay to use this if you're okay with those limitations, those performance limitations. So the super heterodyne, this has been a classic receiver architecture. Some of the pros, so most spectrum analyzers actually use super heterodyne technology. These are some of the pros associated with these are signal quality, very high signal quality, very high signal fidelity, and dynamic range. The cons are the size. Obviously, as you add more filtering, as you add more associated circuitry, you will have a larger footprint. Okay, and then power consumption as it relates to all these circuits. Okay, so let's the final architecture I'm going to talk about is the direct digitization. Now, this is where software-defined radio wants to be. Okay, where you don't have all those LNAs and the mixers. So no mixers, no mixing products. You directly digitize it. So you directly turn an analog signal into a digital one, and from then on, it's all software. Now, this has the biggest pro is one of signal quality. It's excellent signal quality because you don't have any kind of spurious artifacts due to the mixing stages. The cons are the limited frequency range. So these ADCs, they go up in bandwidth. You have multi-gigasample per second ADCs, but you sacrifice dynamic range in the process, as they're only about 8 bits or 6 bits effectively. So you sacrifice, you can get a large, very high sampling rate, but you're going to sacrifice dynamic range, which, as I mentioned, is an important attribute. And typically, to address the frequency range requirements that are required for modern waveforms, you need a very large amount of bandwidth. Okay, and that in turn results in a lot of thermal heat dissipation. So that's a very big con, these two. Now, with the R5x series of products, what we did is actually we implemented a hybrid architecture. So the reason we did this is we wanted to leverage the best, or rather the pros of each of these architectures into one device. So we use a super heterodyne architecture to leverage the signal fidelity for modulation quality for the analysis aspect. We've got a direct conversion receiver in there. So the circuitry is shared. but it does break out into these various modes, if you will. And the direct conversion architecture, we do not use this for demodulation, for instance. We only use it for detection. So the wide bandwidth plays a very big, it gives us the wide bandwidth that's required. So the 100 meg bandwidth as a result of that. And finally, we use the direct digitization with just an ADC over a limited frequency range. So it covers the up to 50 megahertz. So it includes the HF band, and it's very clean down there as a result of that. That trades off. If you were to use something like a super het architecture down at the lower frequencies, you end up with a lot of spurious artifacts that can, as I mentioned, impact performance. So that's why we've used 3 architectures, a lower one for a limited frequency range, and then we trade off between the other 2. And as a result of that, we're able to achieve these specifications. So just a little pictorial view, as I mentioned earlier, for the signal detection aspect, purely detection, we use a direct conversion mode of the receiver. And for signal measurement and analysis, we use the other 2 modes. So what are the main challenges we encounter in a design as such? I'll just go through the high level because there are many more challenges as you break each one of these out. When it comes to frequency planning, the first step in RF design of a receiver is frequency planning. So you plan your local oscillator frequencies, your IF frequencies, multiple IFs, and you plan your pre-select filter bank so to limit the external signals that can otherwise result in spurious signals in the receiver. And all that is done through a frequency planning stage where you plan out where each of these frequencies needs to be. And that's a very detailed process. It's often, you can do it using simulation, but what we've found at ThinkRF is that we have to take a hybrid approach where we combine an analytical phase with an experimental one. So we'll actually look at manufacturers' data sheets, but we augment that with our own measurements. And we perform very detailed measurements to understand the performance of very specific components at all frequencies, so that we can actually meet these spurious targets. So a very complicated process, but well worth the time spent because it gives you a high quality product. And as we all know, simulation doesn't always work. There are factors that you're unable to account for as inputs that simulation. And as a result of that, you always have a certain amount of uncertainty. So this is especially true for RF. People refer to it as black magic often, but it's, if you could account for everything, you would get the right result. But the problem is that you can't always do that. So you have to have multiple iterations to get to the desired level of performance. So a way to achieve our cost targets is judicious use of integrated chips. They're not always a good idea to use integrated transceivers because they do have limitations in performance. Having said that, we have used them where it makes sense, where we can make that design trade-off or that spec trade-off. And finally, we've attempted and succeeded in a fanless design. Obviously, a fanless design is the best. You don't have mechanical failures. I mean, you don't have anything to fail mechanically when you have a fanless design. So and obviously other issues with fans in the field, dust, etc. You avoid that. So this is a challenging one because when you move to a fanless design, you've got to cool everything with pads, with metal. It does add weight to the product. So there is an obvious trade-off over there. This slide here just reiterates what I said earlier, but just gives you a top-down view of some of the other attributes. The real-world operations. So as I mentioned, the fanless design is a part of that. The transmitter location, we enable that with a few different attributes in this product. So one is the GNSS, the built-in GNSS, the triggers, so the ability to use a PPS trigger the device externally to initiate measurements, and the gigabit Ethernet port, which allows you to natively, without the use of an external processor, connect to the network. And then the final attributes are size, weight, power, and cost. Okay, so let's take a look at some real-world use cases finally. This is the last section of the presentation. Here are the family of products that we have. The R5750 product goes from 100 kilohertz to 27 gigahertz. So all in one package, all under 6 pounds. So very lightweight for that performance. The frequency of this product, now we've got millimeter wave frequencies that we need to address. So what we did was we designed a family of, a small family of tuners down converters that go from 24 to 40 gigahertz. So it's easy to take a signal from 24 to 40 gigahertz, convert that down to an IF frequency or an intermediate frequency that can go right into the R5750 and analyze it. And this tuner down converter is a way to upgrade sensors out in the field to make them 5G ready. So if you have an analyzer that's unable to make it to the millimeter wave frequencies, it's a very easy bolt on. Similarly, we have another product that's a lesser performing product than the D4000, which addresses the frequency range of 27 to 30 gig. This was designed primarily for a customer application at 28 gigahertz for one of the US millimeter wave bands. Okay. By way of a real world use case, drive testing is one of them. So this is a situation where you drive around a city or an urban environment or even a suburban one to figure out what your network looks like, what your network performance looks like by way of RF propagation. So these sensors are used to connect. You connect to these sensors with a PC or a laptop, and you collect data using as you drive around the city. So you can do this in a mobile format, as is shown here, where you conduct a drive test and you map it out so you know what your signal strength is at every point along your route. Or the other thing you could do is leave it at a site and let it collect data for a long period of time to understand how the signal varies at a particular location. Now, you might do this at a very sensitive location, for instance, where you want to understand how the signal changes during the course of a day, or how it changes as the environment changes, right? You might have new construction in a space. The third situation is if your cellular network is experiencing interference from a jammer or what have you, or any other source, maybe a leaky cable, you can leave this at a site and log that data. So it tells you when that happened. So it tells you what time of day it happened, what the signal was, what the strength was. And you can't really do that with a spectrum analyzer in the way that we want to. So it ideally functions as a distributed device, or it can also function in a standalone mode, as I've described here. Frequency extensions. This is a product we did for Viavi, for a US customer. This was designed to extend the frequency range, quite simply to extend the frequency range of a spectrum analyzer all the way up to 28 gigahertz. And this was designed in a small form factor for interference hunting, to go along with the Cell Advisor product. But it can also, again, you can see there's a network port here. All our devices are designed with networking built in. So you can leave it out in a remote location to exactly do the same, to monitor over time, monitor spectrum. Now, persistent RF monitoring, this is where you want to measure signals in a distributed manner across an urban landscape. Now, this is going to become very much more important with 5G signals because the ranges of these signals are limited. So with millimeter wave propagation being smaller, if you really want to get closer to understanding the impact of external signals or interferers on your base stations, you've got to start deploying in a distributed manner. in a more granular way. And that will help understand how these systems are performing. We have, we're, as I mentioned, we're getting into completely uncharted territory here with 5G millimeter wave, but this will allow you to do that. And you can watch you can monitor your nodes on a map, and you can you can zoom into any of these nodes to understand how they're performing. Okay, so to summarize the presentation, I covered what was the rationale behind spectrum monitoring? What does it look like today, and what do we expect it to look like in the future? And when I say future, I mean, we're seeing this right now. We're seeing use cases with distributed monitoring, with customers that want the results from nothing else, nothing other than a distributed system of sensors. We want, customers want real-time data. They want to understand how the network changes with time. And there's no way to accomplish that with a truck with spectrum analyzers in it. Even if you left it at a site, it would be very difficult to organize them by way of a network. Then we touched on the requirements for spectrum monitoring, the main ones. I went through the various attributes that are required to address spectrum monitoring in this new world that we live in. With tremendous wireless growth. And what are the receiver architectures? So as I mentioned, all the spectrum analyzers and software-defined radios, they're all at the core of them is a receiver, a very capable receiver. So what do those receivers look like? Okay, by way of architecture, and what have we implemented at ThinkRF? What's worked for us? And finally, I summarized with some use cases, some real-world use cases that the product is used for. With that, I'd like to close this presentation. Just wanted to mention that we are hiring at ThinkRF, so we have a number of career opportunities. Please feel free to check out our website, drop us an email. If this topic is of interest, if you're interested in working with us, we're looking for RF, digital, hardware, software skills, firmware, and a very exciting time. So we'd love for you to be part of that opportunity. So feel free to contact us.